We call them kind of single point of failure attacks. So what we do is for each power plant in the system, we compromise its pressure sensors, and we say that they're reading at a nominal value even when this kind of spike occurs. So if you look at these figures up here, when this period of high stress comes into the system, there's a dip in pressure, right? Because all of a sudden, all this gas is being pulled out of the system, all this gas is being used up to generate more power. There's kind of a dip in pressure, right? And so what happens is we're going to lie at this sensor and say that everything's fine. And the way that the control algorithm works is that it looks at basically all the downstream pressures of a compressor, right? It looks at those and says, okay, I need to adjust by this much based off the disparity that's downstream of me, right? So if we are able to lie about these kind of readings, we might be able to prevent the compressor from ramping up the way that it needs to. Okay, so we applied this kind of attack to each one of the power plants in our system in 6 different runs of the simulation. And out of those 6 trials, 5 out of the 6, nothing really happened. The system was able to carry on. But there was one trial that did cause a failure, and that was when we lied at the Fort Collins power plant. And we'll explain kind of why this happens, but first, this graph kind of shows what happens from that trial. So right about near the end of the window, we can see that the Fort Collins power plant goes offline, and then later on, this Fort Morgan plant finally also fails. So why is this happening? Well, here's kind of a snapshot of the model. So the way that our model is designed is that this Fort Collins compressor is kind of the main line of gas, or it's the main supplier of gas to everything else in the system. So up above here, what you can't see is kind of a Cheyenne reservoir, so it's an unlimited supply of gas. So we're kind of isolating this one section of a gas pipeline. And that gas is flowing through, and this Fort Collins compressor is compressing it and supplying gas to Longmont and Denver on all these areas downstream of it. And then Fort Morgan here on the right is kind of like an auxiliary support system. So what this is doing is it's got some pipelines that cross into Longmont, into Denver, and it can pick up some of the slack if this Fort Collins compressor isn't able to handle the demand. But it's not really designed to carry everything on its own, right? So since this Fort Collins compressor is acting as like a main line of the system, when we're lying about the pressure reading at the Fort Collins power plant, it's preventing this compressor from ramping up the way that it needs to. And as a result, this compressor continues just puttering at its kind of low level. And the gas starts to get evacuated out of this Longmont line and some of these other lines. And so what happens is eventually this plant goes offline because there's no gas being able to be supplied to it because this compressor is not doing its job. And then eventually all the load kind of gets shifted onto this Fort Morgan thing on the right. And this happens because of this Fort Collins compressor not doing its job. And so the load gets shifted onto this, gas gets evacuated out of these pipes, and as a result, the Fort Morgan plant, which is over here on the right, which you can't see in this figure, but that also happens to go offline. So really what this means in this single point of failure attack, so first of all, the caveats are that realistically, yeah, maybe this Fort Collins plant would go offline from this attack, but you would never get to the point where this Fort Morgan plant would go offline because as soon as Fort Collins tripped off, the operators of the system would likely know that something is going wrong, right? And they would be able to make corrections. But what it does inform us that's really useful is that these systems can have certain critical points, right? And maybe this isn't a perfectly one-to-one example of a real system, but there are SCADA systems and ICS systems out there that might be supported by one kind of super node, so to speak, right? And so this Fort Collins compressor is pretty critical in the system in the sense that if it goes down, it's going to bring other things with it. So this leads us to kind of experimenting with a more sophisticated measurement attack. So what we want to do is we figured out that this Fort Collins compressor can be kind of a critical point. So based off that first set of experiments, we know that, and our new objective is, can we design an attack where instead of just compromising one point, we compromise 3 or 4 points and kind of use that in conjunction to cause a failure to occur more rapidly. So kind of we want to keep the Fort Collins compressor from activating. while simultaneously kind of like getting the gas out of these lines as quickly as possible. So how are we going to do that? Well, we're going to lie at Longmont and we're going to lie at Fort Collins to say that the pressure is nominal even though it's not. So if we were able to hack into the PLCs in both these systems and lie about the pressure readings, and then we're going to take this Denver Watkins compressor, if we were also able to compromise those PLCs and lie and say the pressure is too low, what's going to happen is that this is going to prevent the Fort Collins compressor from activating, and at the same time, it's going to cause the Denver compressor to turn on and try and pump more gas to its power plant because it thinks that pressure is low there. So this is kind of what these attacks look like. So here, this brown line is the lie pressure at Denver, so you can see that we're lying and having it be lower than its actual nominal amount. And then this blue and green is the real pressures for Fort Collins and for Longmont. And then this red line and what would be underneath it is an orange line is the kind of lie pressures, which is just holding at a steady 800, which is the nominal value in the system. So what happens? Well, the low pressure at the Fort Collins plant causes it to go offline, and then the following demand on other power plants, coupled with the fact that the Fort Collins compressor is not doing its job, causes the Fort Morgan plant to trip off very rapidly as well. So if we look here, here's our 12-hour window, and we can see this orange line is the actual power generation capacity of the system, and the blue line is the required load. So it's doing well until the end of the window, and then the orange dips down, and what that means is that our system is running at its max, but it's just not able to generate enough power. And what really happened was Fort Collins came offline. This Longmont line and Denver line and all this stuff, Denver started sucking extra hard, pulling gas from Fort Morgan, pulling gas from Longmont, and it caused the Fort Morgan plant to go offline almost immediately as well. So this is different in that first attack in the sense that we were able to cause both these power plants to fall offline in rapid succession. So what happened is Fort Collins went offline, and then about a little bit less than 5 minutes later, we also got the Fort Morgan plant to go offline. And this might not seem with these charts, it kind of seems innocuous, but it does have an effect in the sense that the amount of loss of power generation capacity was about 800 megawatts over the course of about 5 minutes. And this is just power that the system's just running maxed out now, and it just can't deliver that demand. So that means that in a theoretical electrical system that would be partnered with this natural gas system, it would then have to go lean on the surrounding power grid, or things would just, we'd start losing power. So I think that in some respects it kind of is a little bit scary, but there's also some other interesting insights. And so what these experiments kind of tell us is that the single point of failure things are typically not as dangerous as when you can get multiple sensors to lie in conjunction. And that's kind of an intuition about the system, is more things getting hacked into is generally bad, right? But if you had enough redundant sensors in this system, it would be very difficult to get these lies to work, right? So usually popped past the slide. Usually these systems have a lot of redundant sensors. So that means that a hacker would have to be able to compromise a lot of different PLCs in order to make these types of attacks work. And we also kind of have the assumption in our simulation that there was no out-of-band cross-communication. So what I mean is that usually the people who are working these power plants and stuff, like, they'll probably pick up a phone and call either the gas system operators, or they'll be communicating with other plants, and they'll be working together to try and figure out what's going on, right? And that's kind of an assumption that we don't have incorporated into our simulation. But then the lies that come from our sensors need to be sustained for quite a long period of time for these attacks to have any effect. So for example, like in this attack, you can see nothing happened until the end of this kind of window, this 12-hour window. And at the very beginning of this window is when the attack started. So what's happening is that these sensors are being lied about for, like here. So here we can see where this attack really starts to take place is around the first day, right? That's when there starts to be a real disparity between the two, except for this Denver one kind of starts at the beginning. But nonetheless, even though these attacks are occurring for almost 8 hours, nothing happens until kind of the very end of this window. And there's a lot of reasons that this happens. One of them is because there's storage within these gas pipes. So we saw that even when there was no control intervention in the system, the failure didn't occur till the very end of kind of that window. It's kind of the same thing here, that the gas systems kind of just have storage within them. They're not like an electrical grid where it doesn't really have that same level of storage. And that kind of helps them be resilient in scenarios where that increased demand happens very rapidly. And then the other kind of notion that's important for this is that what I find really interesting is that these types of systems might have critical points that are more crucial to defend than other points in the system. And what I mean by that is, if you have limited resources and you can't defend every single PLC in your system, or you can't defend everything from getting hacked, well, maybe you don't have to. Maybe you only have to defend the most critical points in the system, and then you can kind of rely on the resilience of a system in its own right to kind of protect you, right? And we kind of noticed that with this system, that when we were doing our single point of failure attacks, we didn't really have any issues unless we were able to take down that 4 columns compressor, right? And that's kind of the point I'm trying to make, is that 4 columns compressor acted like a critical point in this system. And so that's an important kind of intuition that we got out of this simulation that we might not have been able to get out of testing on a real system or testing with kind of a mathematical model, right? So I think that's where the simulation starts to really add some value, is even if we're not perfectly realistic, even if we have some assumptions, we're still able to kind of derive higher level insights that can be useful for defending these systems, right? But what are some limitations of this simulation work in these experiments? So I talked about one of them, which was we don't have a lot of redundant sensors. We did make some assumptions about the out-of-band communication and people talking to each other. We don't have, so it's also possible for these systems to have large kind of gas storage tanks, and we didn't have any of those in our simulation, but that would have likely made it even more resilient. And then our gas pipes in our system, and I didn't talk about this earlier, but our gas pipes are very large in diameter. So for like this Colorado model, there's like 36-inch and 40-inch pipes, and those are pretty uncommon in the real world. Typically, the engineers for these systems will lay down several kind of smaller pipes instead of 1 or 2 very large pipes. And that's something that we didn't model. That's something that we could model, but that would have an interesting effect, I think, on the temperature of the gas, and also it might actually limit the storage as well. And it's something that we would need to explore in future iterations. And then another important assumption that we made is that I had a pretty intimate knowledge of the system because I was the one who designed it, but most attackers might not know all the intricacies of these systems. They can get really complex on a large scale. And so this kind of sophisticated attacks where you know how things are interconnected and what's going to happen where are a little bit superfluous in the sense that you know more than maybe the typical attacker would, but it doesn't necessarily mean these insights are any less valuable. So some of the future work for this kind of project, we want to look into modeling network protocols and network behavior, something I talked about earlier on in the considerations. Finding a way to synchronize everything so we can resolve some of those timing issues in the simulation. Integrating hybrid and real PLCs, which we talked about quite a bit. And then some other interesting things. So remember earlier I talked about, in our first experiment, I talked about the pressure and temperature not varying together when we were using that when we were lying about the pressure. And I think it'd be an interesting case study to try and find a way that you could use machine learning or data analysis to discover constraints that exist like that. And then you could determine if something was faulty, because you could say, okay, pressure and temperature normally vary together in the system. Or these 2 power plants shared, a successor line, so their pressures will likely vary together, right? You could find a way of automatically discovering those constraints, and that could allow you to kind of know when something is is not following those constraints and give you insight on maybe if a sensor is faulty. Then trying to design and implement some encryption schemes so that we can basically, since we're using a simulation, there's no harm in us creating an encrypted Modbus and seeing how it would affect or how it would allow us to defend these attacks or how we would do key distribution. All these things are possible because we have a simulated environment where we can kind of play around with these different ideas. Then we want to create some more physical models eventually, so not just model gas pipelines, but see how our simulation looks with an electrical grid, or maybe integrating both electrical and gas pipelines together. And then also, like I said, I talked about this critical point thing in the last couple slides, but if there were a way that we could automatically discover a critical point in the system and figure out, okay, this point's going to be crucial for either delivering gas or delivering power or doing whatever it does, and an attack on this point would be particularly damaging. An automatic way to discover that would be a super valuable tool for defending these systems. So ultimately, our conclusions from my work, I think, are that the simulations that we've done, even in their kind of infant stages, they can lead to some interesting insights about the way that these systems work. And it gives us a lot more firepower for exploring ideas than just kind of thought experiments and the limited kind of stuff we can do on a real system. So like I said, it allows us to play around, it allows us to experiment, it allows us to do a lot of things that we wouldn't be able to do before. And I think this measurement attack thing is a really good case study of that, in the sense that, okay, well, what happens if you start playing with the sensors on purpose to try and break the system? And we saw that that can actually have some negative effects. And although we have some assumptions for how we got there, I think it's still an interesting experiment, because it does give you some insights into, okay, like, you know, we have to consider that the sensor's data is legitimate in these systems. We can't just ignore and assume that everything's going to be all right, right? Also, I think with our work, we've kind of shown that simulation for these systems, even though they are sophisticated and even though they can be difficult to simulate, it is possible, right? And there are some caveats. We have some inaccuracies in some places, but it is possible and it is useful. And then finally, this has more to do with kind of the experiments that we did, is that gas systems react very differently than electrical systems do when it comes to these types of cyber attacks, and that kind of has to do with the storage in the system, right? So like when a power grid goes offline and there's a blackout, it usually occurs within minutes. What we saw in our system, even when things were faulty for 8 hours, the system was still kind of chugging along in a lesser capacity until it finally kind of failed. And so I think that's kind of the final insight to get from some of this gas versus electrical system comparisons. Other than that, I figured we could use the kind of rest of this time to kind of discuss and talk and ask questions. But before we get into that, I just want to say thank you so much to Dr. Ray and to Dan and to Dr. Gersh, Dr. Young, Jerry, and everyone here, especially Luis and Saja, who are going to be carrying this work on. And I really appreciate just all the effort everyone has put in to make this project a reality, because I think that when Jerry and I were drawing this up on a whiteboard like 2 years ago almost, I never really thought that we could create something so interesting and really be able to do something so cool with it. So I really appreciate you guys. All right, so anyone have any questions?
I'll start off, Brent. This is Dr. Gersh for people who don't recognize my voice. I don't know if real world systems have the equivalent of Byzantine types of protections built into them with multiple sensors. As you said, in your systems you built, there was one sensor and you had to trust it. And you had an oracle that was ground truth, but it wasn't really a fault-tolerant Byzantine type arrangement. I'm really intrigued by the thought of the sensitivity analysis is what I'll call it. What are the critical points in the system? The Fort Collins generating plant you brought up is one. Do you think it might be possible to take this type of simulation and do what I would call the equivalent of a fuzz test, just like you do fuzz testing on networks, fuzz testing on software, where you give it all sorts of inputs and actually detect what the sensitive points in the system might be, or is that just a pipe dream?
Oh, it's definitely possible. We just have to anything. Oh, the cheesy answer is anything's possible. No, with this system we could do it, right? Because we designed it to be
Cheesy.
modular, right? But no, I know. I think what you're getting at is there a way we could kind of screw with these all these sensors kind of in an iterative and in controlled fashion to see
Well,
kind of
no, and then actually in an iterative but random fashion
yeah.
to detect interdependencies and things. That's what the whole idea of fuzz testing is. You give all sorts of random strangenesses into a system and see how it behaves.
Yeah, so can we kind of stuff random inputs out of these sensors and just see what happens, right? So we could kind
Yeah.
of run trials and trials and trials. Okay, we're going to
It's just
fuzz this one. We're going to fuzz this one. We're going to fuzz this one and see what happens. It would definitely be possible.
yeah. So the question is for future work for Luis and Saja, is your system already built in such a fashion that they could do this sort of an experiment?
So the way that we have it set up right now, and how I would do it. So the way that we are specifying compromises in my work was that we were using basically a mathematical function, and this is just kind of interpreted by the Python interpreter. So in theory, like if you wanted to fuzz a sensor reading, you could do that in a mathematical standpoint, but we wouldn't be able to do like we wouldn't be able to send it things like a string, right? It would just be binary data, but we could in theory do like a random function coming out of a sensor and kind of just see what happens, you know? So like we could kind of do this kind of process where we would run a number of trials. So we would have Fort Collins plant and we would kind of fuzz that data coming out off the sensors into that PLC. And then we would fuzz Fort Morgan, then we'd fuzz Denver, and then we would fuzz Colorado Springs. And we kind of iterate like that. And then you could kind of do like, we're going to fuzz 2 at once. We're going to fuzz 3 at once or something, right? So there's ways you could do it like that, I think.
All right. I've got 2 other quick questions, then we can move on to other people. The Simulink that you used, the simulations I've mostly done in the past were not continuous simulations or MATLAB based, but they were like discrete event simulators, similar to GPSS or other type things. MATLAB and Simulink can be run in a discrete event thing. Would that help in any way in improving the system for putting things on event queues as opposed to running it strictly through time?
Yeah, I think that's kind of the direction you would want to go if you wanted to kind of really get this thing. Um, I think that has a lot of value, right? Because the way that we're playing with time right now is kind of fast and loose, and I think it leads to some can lead to some serious issues later on. And I think, and Dan knows better than I do about the nature of Simulink, but the way that we're doing it right now is it's like partially continuous and then like partially just discrete, right? So it's
Yeah,
a little
that's what I was
janky.
thinking.
But I think that if you could go full discrete, that actually it might be better, but I don't know.
Okay. Well, a lot of the reason I'm asking questions like this is this is your oral exam. We got to see how you defend yourself. Last question is just recently, like within the last couple of days, in line with your future work again for network faults. It was just revealed by Wired magazine of the thing called Ripple 20. I don't know if you've heard of that or not. It was discovered by an Israeli cyber security research firm where a company named Trek, T-R-E-C-K, they built a TCP/IP stack used in SCADA devices. I have billions of IoT devices built by reputable manufacturers around the world that just incorporated it into their embedded operating system. So they use this Trek TCP/IP stack, and they found 19. I don't know why they call it Ripple 20 because they only found 19 vulnerabilities in which they could take over the device and then do command injection and stuff like that. So this is not really a question for you because I'm assuming since it only came out 2 days ago, you haven't done anything about network attacks, as you said, but just as a direction that Luis and Saja might want to look at in the future and check out this type of Ripple 20 attack and kind of things it can do.
Yeah.
What's that?
Interesting. A network attack in a SCADA system.
Yeah. So that was more of a comment than a question.
We could definitely get that software and see if we could kind of see if we could find that tool and kind of build our own sandbox around it. And then whether we have a virtual PLC or we go and get a Raspberry Pi or something, And
Oh yeah, they've got all sorts of demonstrations on the Israeli website that shows how it can turn off a I can't even pronounce the word uninterruptible power supply, and do all sorts of weird things.
that's pretty. It's pretty. Yeah, it's amazing that a lot of cyber attacks kind of rely on people's trust.
Yeah,
You know.
yeah, exactly. Anyway, let me pass the talking stick on to someone else.
So, Brent, I guess this is not pertaining to your work, but so one question I had was, as you mentioned, in cyber physical systems, there are often redundancies like temperature, and there are correlations between attributes by which, even if something were to, show a compromised value, you can, there are other checks and measures which kind of, are there against which you can validate, find out anomalies. So I would like to go back to your point that multiple sensors and multiple things must be compromised for something to happen. And I don't know whether this is a question to you or to Dan. So how likely, and here I'm talking about insider threat. So how likely is an insider possible for an insider to have access to, say, maybe the Fort Collins, some sites, Fort Morgan sites, and some other, sites, or multiple PLCs? So how likely are those actually? Is it very much possible, or is the infrastructure sort of compartmentalized so that there's no rippling effect and things like that? So do you have any knowledge about that?
So I think Dan can probably answer better than I can, but to my knowledge, I don't know enough about the way that people in these kind of environments work, right? A lot of what I do is trying to figure out how to simulate the kind of dynamics of the systems and the cybersecurity standpoint, but I think maybe Dan can answer that better.
Right, and that might, have some effect on your simulation as well, because then you would require, like as you said, multiple compromises. But if they are contained or something like that, I don't know, that might translate into something, and then it might be harder. It'll be more realistic, but of course, more harder to bring something down, which sort of accurately reflects the kind of the real world. Yeah. So that was just a thought I had, while you were doing a presentation.
It's an interesting question. It'd be one to ask with a group of people from industry in the room at the same time, right? Mm-hmm. Because a lot of these systems are aggregates of many acquisitions and divestitures, and as a result, they have many different vintages of systems, and they may be kind of poorly connected to each other, that type of thing. But on the other hand, there may be a lot of really old equipment that's very poorly secured and is only protected by some kind of a firewall or some type of a barrier to entry. But on the other side of the barrier to entry, it's actually quite weak. Mm-hmm. So, but I think that unlike the electric system or the telecommunication system, where assets do not change hands very frequently, in the gas system, assets actually change hands quite often.
I see. Okay. Thank you.
What do you mean gas assets change hands? You mean companies buying companies, or?
Yeah, companies buy companies. Mm-hmm. They also split off lower performing assets, on a regular basis, and sell stuff where it's very unusual for electric operations, which are usually kind of controlled utilities, to actually get rid of some asset. So,
mm-hmm. Okay.
I am going to drop off because I have a call at 2:30. So
sounds good.
Brent, I think the one question I would ask is I think that you had done some work on the behavior of other systems with respect to cyber attacks, period. And then you got this system running, and its behavior was a bit different than you expected, right? And so to what extent do you think that sort of, kind of the other attacks that you had worked on or you'd read about, how did those compare, and how did that write-up compare with what you saw with the dynamics of this system?
So I think, again, I think the most surprising thing to get from these simulations is that I don't think that the gas system is as fragile as, in a sense that, as like an electrical system maybe, in the sense that one wrong move could cause a lot of cascading failures. I'm sure that I could be wrong in some respects about that, but I think that like a lot of the things that surprised me about this system is how slow moving everything is, if that makes sense. So again,
Sort of
like even if you
low
did
pass filter with a capacitor.
yeah, so like even if you were to do a command injection attack, right, and you were to start forcefully manipulating things, there would be a delay in the way that the system reacts to those attacks, right? And so I think that at least gives you some time to either deploy countermeasures or to deploy defense. Whereas an electrical system, I think that if you were able to start to trip things and start to mess around with things really quickly, you could start to cause damage really fast that would cascade. And it's not necessarily always like that in these systems. And I think that was, I guess, the most interesting part when I started playing around with this in particular.
Right. Your intuition doesn't translate really quickly between electrical systems or telecommunication systems and gas, right? Because the timescales are way different, period. But it also could be that the control system and the sort of the mindset of how the systems are controlled are relying on that. And so they may be vulnerable in really unique ways that wouldn't be seen in the electrical system because there's so much time, right? So things that are automated in electricity or automated in telecommunications may still be manual in gas systems just because they're so slow. So,
yeah, that's a very good point. And I think that also, in some respects, opens up unique attacks in the sense that people are oftentimes the most vulnerable part of a system.
Mm. Yeah.
I'm sorry that I have to drop off, but I have another meeting. And good job, Brett. And it was glad I joined to hear your presentation.
Thanks, Dan. We'll see you around.
Thank you.
So, any other questions from the audience? Because, yeah, sure. Go ahead.
Yeah. Brad, what's the actual benefit when we add physical PLC aside virtual one with the simulation?
So, I think when you're adding these physical PLCs, it just gives you so much more accuracy and so much more fidelity in the sense that, so like our virtual PLCs really are kind of just like a Python Modbus server, and we can kind of make some alterations, but we rely on the fact that, okay, someone has compromised it and they can do this to it, right? But it would be really cool if we could hook something up to the system that's a real PLC, and then we could actually attack it. And an example is like sometimes these systems aren't as bulletproof as like we would hope they would be, right? So when we were playing around with the lab jacks at the METEC site a while back, and I don't know if I'm allowed to disclose this, so Jerry, you can stop me if you want to, but like they had like a legacy HTTP server on these lab jack devices, and they were gonna like kind of add this kind of data exfiltration over HTTP so you could like read what was going on in the controller and stuff, and then they just never finished that functionality, but they also didn't remove it. So it's one of those things where it's like there's these weird kind of little like quirks and fingerprints that might exist in these real PLCs. And those are things that an attacker could take advantage of, and we might never know about them or how they play into the kind of bigger picture without being able to actually get a real PLC in our hand, right?
Yeah, because you certainly didn't put it in your simulation.
Yeah, because how would we know to simulate a thing like that, right? And then the flip side of it is like, and I think this was Jerry's idea, I think, but taking a physical PLC doing penetration tests on it, figuring out some of those quirks, right? Figuring out some of the things that might cause it to malfunction, and then trying to replicate that in a virtual representation of whatever PLC that is. So that would be like a really interesting work in seeing if you could kind of model an existing kind of physical controller as a virtual replica.
Oh, okay.
Any other question from the audience?
Yeah, I would suggest you do ask questions, because if you're going to carry on this as future work, you want to understand this as best as you can.
Mm. When you talk about the gas and electrical system, in your thought, you think electrical system gas system?
I'm sorry,
we
can
can
you
work more
repeat
in
that? I think we had a little audio malfunction halfway through your question.
When you compare gas and electrical system, as I understood you, the electrical system more vulnerable than gas system.
I wouldn't necessarily say more vulnerable, right? It's a better way to put it, and I guess what I was trying to say earlier is that the nature of the system is very different. So I think Dan just put it really well in the sense that, okay, so the gas system, the timeline is much slower than the electrical system. And what that means is, like, if you were to take out a compressor station in the gas station, let's say, and it was just to turn off, things might not fail immediately because there might be enough gas in the pipes and in storage that can keep the power plants running for a little bit, right?
Mm.
But if you were to take out a transformer or a very large power line in an electrical system, that's going to have an immediate effect on the surrounding area and possibly on the surrounding region if that is enough damage, right? And so I think that's where I say, I wouldn't say the electrical system's more fragile, but I would say that everything happens much faster, if that makes sense. And I think that in some respects, because the gas system has storage in it, it does add some resiliency, I think.
Okay.
Any other questions from Saja, Lewis, or Erica? Jerry?
No, for me, no. Thank you, Brant.
Jerry, Lewis, Erica, do you have any questions?
Thank you. I think it was really good.
Thanks for attending, Erica. I appreciate you coming.
What about Jerry and Lewis?
Yeah, I don't have any particular questions. Of course, lots of comments on the other questions that people have been asking Brand, but that's not actually overall, Brand, you answered the questions such as Joe's question on integrating distributed simulation into the system. You answered that quite well. I fundamentally think that we're ultimately going to end up with a hybrid. And the continuous event simulation, the Simulink world is going to be focused more on the physical side, the physical modeling side. And I think we can use discrete event simulation quite well on the network modeling, and then also using that to tackle this concept of time, which is still something that gives me gray hair when I think about it. And I also firmly believe that Dan's comment about the quote-unquote control system on the gas pipeline side has a lot of manual steps in it, and that we can turn that around and say those manual steps are taking advantage of the much slower response time. Whereas if you're having a human in the loop on an electrical system where a fault could cause a blackout in milliseconds, and you just can't do it. So I think there's a cultural buildup of, or because of the nature of the gas system, the control systems have some inherent vulnerabilities that if we were to put our black hats on, we could take advantage of, I think, or put our white hats on and suggest areas for improvement.
Yeah, I think that's a really interesting insight that I hadn't really thought about before, but definitely the aspect of manual operators being at the core of some of these gas systems in comparison to maybe some more automated components in electrical systems um, is an interesting vulnerability. And like I said before, I think cybersecurity is such an interesting thing because it's more than just computer systems. It's also the human beings who interact with those computer systems who can be at fault for some of the things that happen.
Yeah, and then also turn that around and say, does having a human in the loop in the decision-making process add intuitive behavior / some form of better response than an automated system would?
Yeah, I agree with you. I think turning around is interesting too. It's I think there's trade-offs, right? I think the trade-offs exist, and I think again, gas system can have someone making those decisions, and they can have that process of, like I said, that out of band communication where they might be able to communicate and call each other and figure out what's going on, and that's almost a luxury that people working in these systems might have that other technologies like telecommunications and electrical might not have.
Okay. Any other questions or comments? So if there are no other questions, I'll ask the committee, members to remain, and all of you leave off, including Brandt. And Brandt, you can rejoin, after I give you an email, maybe.
Okay, sounds good.
And we can ask